Alright, today we're going to talk about finding the area between two curves. Sometimes more than two curves, but usually two curves. So in this drawing, it sort of looks like a little bit of a birdie. We've got two curves. We're going to call this one f of x, and we'll call this one g of x. And so we know that we can use the integral symbol to find area. And so on this problem, we're just going to set up a couple things. Let's say that these two curves cross at A on the x-axis and at B. Well, then if we want to find the area that's trapped between those two curves, we want to squiggle between A and B. And if you think a little bit about finding area, really what's going on here when you do an integral, it's almost like you have a bunch of these little orange rectangles. You know, let's pretend that we had like thousands of these. You know, maybe there's one here, and maybe there's one over here, and so on. But let's say that we just have a ton of them. Well, for each rectangle, if we make them super duper thin, we could measure their width on the x-axis. And whatever difference between these two numbers on the x-axis, that would be the width. And so we can call that dx. That's just standing for like the difference in x. And then for each rectangle, we could find the height of the rectangle by taking the top of it, which would be the top curve, minus the bottom curve. And so if we set up this little equation over here, what this is saying is that if we subtract f of x minus g of x, that's like the height of a little imaginary rectangle, and dx can represent the width of it. And of course, if you multiply the height times the width of a rectangle, you'll get its area. What the squiggle does is it says that we want to sum up all the rectangles from A to B. So really this is like a super Riemann sum. And that's how we find the area between curves. We basically always just take the top curve minus the bottom one, and we do an integral from A to B to find it. So here's a couple of examples. Let's say this problem is sort of set up for us. It wants us to find the area from 2 to 7. So it's talking about this area trapped in here. So if we just draw maybe one rectangle, whoops, to help us visualize, that is a horrible rectangle. We draw one rectangle to help us visualize. We're going to go ahead and now sum up all the rectangles from 2 to 7. We're going to take the top curve, and we're going to subtract the bottom curve. And I think you should put that bottom curve in parentheses. If you don't, then you're risking where you might not distribute the negative sign. You might mess things up a little bit. Now to solve this one would be pretty easy to just go ahead and run through a graphing calculator, and we could just go ahead and we could either graph this whole monstrous equation and then shade it from 2 to 7, or we could use alpha window on our calculators and just go ahead and type that in and find it. So we're going to let that one go for now. Here's another problem. Same kind of deal here. I'm trying to find this area that's trapped in here between the two curves. So if I draw a rectangle, it doesn't matter where I draw it, it just helps me visualize. Here's the top curve, here's the bottom. And so I'm going to do the integral, top curve, minus bottom curve. So remember, every time, top minus bottom. Now on this one, I've got to figure out where these two curves cross, because it's not given to me. Last problem, it said shade it from 2 to 7. Here I've got to figure it out, and it sure looks like it goes from -2 to 3. But to confirm that, what I could do is make the two curves equal and solve it. And so when I'm doing this, I'm seeing where they cross. And so I can solve that by getting everything over to one side and factoring it. So sure enough, I was right, because we never really want to just look at a picture and go, oh, I think they crossed at 3 and -2. We definitely want to have, we want to back that up. Now this is another problem. I could use my calculator, and I could run it through, but also it's going to be important to know how to do it without a calculator. So if I'm doing this without a calculator, I'm going to take the antiderivative, and then sadly for me, I'm going to have to sit here and fill in all of this information. So I'm going to plug 3 in there, subtract, and then I'm going to have to plug in the -2. So I don't necessarily have to do this for a ton of problems, but I definitely want to do it for some problems to make sure that I'm okay with it. So you might have to make common denominators or something, but you'll end up with 20 and 5/6. Alright, another example here. I've got to read the problem carefully so that I can sort of work out what it's talking about. It says y equals 2 on the top, y equals x on the right, 1 over square root of x on the left. So it's talking about this region. If I draw in my rectangles here, we've got a problem. Because if I draw the rectangle here, then the top of this is going to be 2, and the bottom is going to be 1 over square root of x. However, if I draw my rectangle in over here to the right, I get something different. I've got 2 on the top, but when I subtract the bottom, that's just x. So that's okay, that's going to happen sometimes. So this problem really had to be split up from 1/4, just trust me on that, until 1. The top minus bottom is 2 and 1 over square root of x. But from 1 to 2, the situation is different. And so what I have to do, unfortunately, is do both integrals and then go ahead and solve those. Now, whether I use a graphing calculator or whether I do them by hand, it doesn't really matter, but it wouldn't be a bad idea to get that practice doing this the long way. It's a little tedious, it's not really the most enjoyable thing in the world, but it's good practice. And so as I plug these numbers in, I'll end up with a half here and a half on this side and 1. I'm not showing all the work there, but if I plug in the numbers and subtract and do all that business. Alright, one last example. Now sometimes we might have a problem where we don't even know what the graph looks like. So we could guess here. We could guess which graph is the top and which one's the bottom. I can definitely find out where they cross. Now we're going to find out as we try to solve this that this is really a problem where we would have a calculator. You know, this is a little bit too sketchy for me to have to figure out the square root of 20/3, and it's going to make things pretty ugly. So this is really more like the kind of problem where we'd have a calculator. And like I said, I could guess the top and bottom, but you know what? I can sketch this. 10 minus x squared is going to be a parabola, looks something like that. 1/2 x squared is going to be a parabola, looks something like that. So I can make the sketch pretty easy to figure out which one's the top and which one's the bottom. Even if I couldn't figure out which one was the top and which one was the bottom, you could just give it a shot, and if your answer came out negative, that would mean that you had them reversed. And so you would just go ahead and sort of doctor it up a little bit. We'll see that on some other problems down the road. So this is one I'd probably just shade on my calculator and get 34.427. So remember, the secret to finding the area between two curves is get a picture, figure out where the area starts and stops, and then set up your equation. It's always going to be top minus bottom for these problems. We'll look at some other types in the future.